Yeah, so I've seen a lot of YouTubers lately talking about AI coding, how it sucks, how they are going back to writing code by hand. If you're watching this video, you've probably felt that too. And to be honest, this has been something I felt since the very beginning with AI. So it felt really great when it worked, but you quickly grind to a halt, and I always thought there must be a better way. So if we look at the current tools that we have at our disposal, like Cloud Code and Cursor, these out-of-the-box tools, they work for kind of these demo projects, right? Creating a to-do list, but when applied to real projects, they quickly fail. And it feels like playing a slot machine. You don't really know what's going on. You don't really know how it's happening. Sometimes it works, sometimes it doesn't. And especially as the complexity grows, we see the cost of change quickly increasing. So we lose control, the cost of change skyrockets, and basically as complexity increases, we lose any benefits that we had from the increase of speed. And actually, this is not only anecdotal, but that's also something that the latest DORA report emphasizes. So if we look at this report, what we see is a high correlation between AI use and software delivery instability. We do see an increase in software delivery throughput, but actually the correlation with the instability is much higher. So instability in the software delivery means software gets pushed to production, but once in production, we see there is something that doesn't work as expected, so we need to rework it. We could think that the throughput could make up for that, right? So we have more instability, but it could be worth it because we are so fast that we can quickly fix the bugs that the AI generates. But actually, what the report finds is that this instability negates any perceived gains in throughput. So to understand why this happens, I think the easiest way is to compare how LLMs generate code versus how humans go about software development. So if we look at humans, we take small steps, right? So we write some small piece of code, we look at the output. Even if we don't write unit tests, we still throughout the process verify that we have not broken anything important and that the code still works. LLMs instead, they just guess what the final code will look like. And this is of course by design, this is how they were trained. But in the end, the result is that LLMs implicitly assume that they will be always right. What they produce is correct, both technically as well as functionally. Whereas humans, especially expert humans, they assume that they will make mistakes. So they work in a way to catch these mistakes. So you might say, but couldn't we solve this just by scaling the model or scaling the inference time? And you might think this is the bitter lesson, right? The handcrafted processes that were very popular in AI quickly got surpassed by much simpler algorithms but that could scale infinitely. While this has been true historically, I want to emphasize in which context it was true. So if we look at the problems where this has applied, they are very decomposable problems, right? So for example, in games like chess and Go, we have a way of verifying, at least theoretically, what a good state is, a good game state is, from the trajectories that it generates in the game. So in the end, you can determine what a winning state is and what is a losing state. And from that, you can trace back the game states that are better, so that favor more game states that are winning versus more less game states that are losing. And the same for next token prediction. So how LLMs operate. It has been a great domain for scaling because First of all, you have a lot of text that you can train them on, and also you have a very verifiable way of telling them what is good, what is bad. In contrast to that, I believe software development has an intrinsically irreducible iterative nature. So that means we cannot, even from a theoretical standpoint, evaluate the goodness or badness of a state just by looking at it. Because being such a complex system involving users, external libraries, etc., we don't have a strong way of verifying that the stuff works without actually testing it. So this makes it unscalable, basically. We cannot really learn from vast amounts of data in this case, because generating that data is incredibly expensive to do. So this relates also to a fundamental limit in computer science, the Amdahl's law, which also shows the maximum speed up that we can get from parallelizing a process. So what we see is if a process has a very big parallel portion, we get a lot of gains in parallelizing this process. And this is analogous to what AI does, right? So it can scale, LLMs can scale very quickly. And I do believe we have seen this exponential growth. And now we're in this phase where we see this lower returns on investment. And software development, on the other side, we see the trajectory is much more similar to this blue line down here. So where we see some gains, but not really an exponential growth. So this is also confirmed by the DORA report. Also, this graph is an idealization because it doesn't consider any integration tax. If we also integrate this variable, we see processes can even become worse as we parallelize them. And in software development, this tax would be basically the review cycle. So when AI generates code, we also need to review it. And just going for this parallelization approach of generating all the code at once actually doesn't pay off. What we see this Faros research also confirming is that we have indeed an increase in the output of developers, but also the review time of this code increases drastically, basically negating any gains from it. And in fact, we don't have any measurable impact at the organization level from using AI. So for these decomposable processes, what we see is that we gain speed by doing multiple things at once. Whereas for iterative processes, what we expect to see is not really to gain much from just doing more things at once, and actually the most performance gains come from increase in quality. And this is also confirmed by DORA. So what we see is no trade-off between speed and stability, which also confirms this hypothesis that software development is intrinsically an iterative process that cannot be decomposed and parallelized. So to underline again, what we see the main issue being in using AI for coding is that being that software development is an iterative process, these errors compound, negating basically any speed gains that we get from writing code faster. But actually, this isn't a unique problem for software development. Actually, this is at the heart of any manufacturing process. And I think looking at these two examples, how Ford versus Toyota approach the manufacturing process is very illuminating also for software development. So let's look at Ford's assembly line system. It is a system which was designed for mass production, and you had workers in these assembly lines, each doing their little job and just caring about one thing at a time, and it led to an increase in speed and volume of output, but at the cost of quality and flexibility. In fact, quality was ensured through an external process. So it was a responsibility of external inspectors, which at the end of the assembly line would then verify what the workers would have produced. And this is very similar to how a waterfall model works in software development. So you have a very sequential process like the assembly line, and the quality is in the end a job for quality assurance teams and not for the developers themselves. So in contrast to this, what Toyota did was to build in quality by design. So they based this on two principles. The first one being Jidoka, and which is the principle of stopping the production line as soon as a defect is identified. So this has the goal to prevent errors from spreading down the line. The second principle, called Pokayoke, is to design processes in a way that prevents defects from even occurring. So by eliminating this defect, Toyota was able to accomplish was faster, more efficient, and more responsive production. So if we look at how we can implement these two principles to software development, we first need to think about what are defects in this context. So defects are always a wrong assumption of some kind. So it can either be a technical assumption, I think that this code will produce this output, but it doesn't, or functional, meaning the code works, but it doesn't do what the user wants. So let's look at these two types of defects separately. For technical assumptions, this software development is actually very similar to scientific discovery. So in the scientific method, what we do is we observe, we formulate a hypothesis, and we propose an experiment, right? So after that, we review the results of this experiment and we iterate upon it. This is how we gain knowledge on how the world works, and we should apply this also to software development to understand how the code works, right? So the analogy or the counterpart, the software counterpart to the scientific method is really test-driven development. So being test-driven means that you write the tests first. So what you do is you have this initial red phase where you write a failing test. This is analogous to the hypothesis. You then write the code to make this test pass. And you then observe basically what the outcome of this code is, and verify that it actually does what you thought it to do. So actually this research by IBM was very interesting because an inexperienced team realized 40% less defects in their code when compared to an experienced team who didn't use TDD. What about functional assumptions? So ensuring that the code does not only work, but it actually does what we want it to do. So for that, the principle is to prevent miscommunication. And in order to prevent that, we need to kind of define what is the functionality that we actually want to achieve. And we call that a contract, which we define before the implementation even begins. Thanks to the contract, we can then develop the implementation in parallel because we have defined the seams between the different layers of our application, and we are able to basically not care what the other layers do as long as they fulfill the contracts that we have defined beforehand. So at this point, you might ask yourselves, why even use AI? If we have test-driven development and we have contract-first design, why not just follow these practices and that's it? And I believe LLMs do have a use case still, because if we look at this research that was done in the University of Lugano, what we see is that 70% of the time is dedicated not to writing or editing code, but actually to understanding what is going on. And I think the bottleneck for understanding is actually cognitive load. So you cannot fit everything inside your head all at once. And I believe LLMs can help alleviate that. So if we look at the types of cognitive loads that there are, we have the good, the bad, and the ugly. So the first type of cognitive load is the good types. This part is directly correlated to the active process of learning. So it is actually the type of cognitive load that we want to maximize, right? The bad type of cognitive load is the extraneous one, coming from the way information is presented to us. If it's difficult to understand, if it's difficult to even gather this information, then we have a high extraneous cognitive load. And the goal is to minimize this type of cognitive load. And what we then have is the intrinsic cognitive load, which is related to the difficulty of the problem itself. So we cannot really increase or decrease this complexity, we can just manage it. So the core idea is that AI should be used as a pair programming partner. So in pair programming, you usually have a navigator and a driver. In this case, we would mainly take the role of a navigator, more responsible for strategic oversight, and the driver is more involved in the technical aspects, in the writing the code itself. How AI can help us in these three ways. So first of all, minimizing the bad, helping us retrieve information efficiently and follow these processes, test-driven development and contract-first design without being weighed down by the cognitive load of following these processes. Also, it helps us managing the ugly, so the intrinsic difficulty of the task, by breaking it down into smaller parts and helping us manage them. The result is more time spent in the good cognitive load. Yeah, so after talking all this theory, I want to show you actually in practice how I envision this working out. So what I've done here is I've created a proof of concept for this contract first test driven pair programmer, and it is in this implementation very simple. It's just two prompts which you can go in and copy, and you will see how immediately how it differs from let's say traditional coding with AI. So let's try to ask it to create, for example, a snake game with roguelike elements. Okay, so what you will see is the architect will follow a contract first design. So what makes this approach unique is that each iteration, each response of the AI will be an action plan. So you will, in the beginning of the plan, you will have a rationale of what this plan is about. This helps you as a user follow the reasoning behind what is going on, and also for the AI, it's very useful to keep trace of this reasoning. Then after the rationale, you have the actual plan broken down into steps. Each step you can checkmark once you have done it. In this current implementation, as it's just a proof of concept, you basically have to go through it manually and implement these changes. So I've moved now into this test directory to show you how you would actually implement this plan. So for example, here, the first step is to create this file. So you can very easily copy, for example, the name of the file, paste it, and copy the markdown that the AI has given us. So we start with that, we can check mark it, and then you will see they ask us to approve it. So we can see here the concept that the AI came up with, and we can now iterate upon it and kind of explain more about what we have in mind and define this overall, let's say, contract of what the game actually should be. So what the AI now expects for each of these steps is to get feedback if this has been implemented or if we have any feedback. The AI will then follow the next steps in the workflow that we have defined, and basically we can follow through this. So analogously to before, we can copy the names and directly create these files. So the developer prompt instead follows a test-driven development cycle. And here you see, similarly to the architect, it does not spit out a straight implementation, but it proceeds in iterations. So we will see, first of all, we will create this test, which we can do as before. And you will see we expect this test to fail. If we run this, we will see this test failing. So we will see, based on that, on the feedback, it will then proceed and propose next steps based on that. Going back to the repo, you have a good summary of the design principles behind these prompts and what the workflow for each is. You have different types of plans that the AI can choose to do, and within those plans, you also have types of action for each. This is just a proof of concept right now, so it's quite limited. It's mostly tailored to be used on Google AI Studio, both for the models as well as the interface itself. And you have to execute these commands manually. The plan is that in the future, there will be a script where the AI at the end of the plan will output a YAML file containing all of the steps and all of the variables, which you can then copy and execute them directly within your workspace. Also doing it step by step and being able to each one approve or disapprove before executing. And also something that I foresee for this project is a dedicated interface. So for example, using LibreChat to implement that. And this would also have the benefit of being able to utilize mixture of agents architecture to break up this big prompt into sub steps. So, and here is where your contributions comes into play, because I've been playing with it since a few months now, but I'm just one person, so it would be amazing if you could try it out and let me know in the comments what your experience was. If you have any recommendations or any feedback on this, I would greatly appreciate it. So one final thank you also to David Farley, because a lot of the content for this video and the inspiration also for this workflow came through reading this Modern Software Engineering book, which I also highly recommend if you want to dig deeper into some of these principles, especially test-driven development. So thank you very much, and I'll see you in the next video where I'll do a walkthrough with using this framework to actually build something in real time.